Hi there and welcome to another tutorial for the Edexcel Further Pure 1 Maths A-Level course. In this tutorial we're doing another lesson on matrices, and in particular how matrices can be reflected, can represent linear transformations. Just to make clear what we've done in the Edexcel specification, we've done all the basic algebra that we can with matrices. We've added and subtracted them, multiplied by a number, we've multiplied matrices together, and in effect we've worked out how to divide by a matrix by finding the inverse of matrices and using the determinants to do that. Now we're going to move on to matrices and how they represent linear transformations. In this particular video, what I'm going to be looking at is linear transformations of column vectors in 2 dimensions and their matrix representations, and we're going to work through the rest in a few more videos to come. To start with, what is a transformation? Well, hopefully from GCSE you remember there were 4 types of transformation that you learnt about. There were 4 types, and these were, the first one was translation. This was where you moved a shape or a point to another point. The second was enlargement. That involved making a shape bigger or smaller. The third was rotation, and that involved twisting a shape or turning it. And the fourth involved reflection, which involved drawing a mirror image of a shape or points in a mirror line. Now, I just want to tighten up with some notation what I mean by a transformation. And let's just pick, for example, let's just talk about a translation for now. But what I'm going to say here will apply to all the others in the definition I make at the bottom. Say you've got yourself the XY plane. This is X, this is Y. I'm going to call this the XY plane. It's all the sets of coordinates in the XY plane. Now, say I took myself, let's say, a square. Let's put the square over here. And I'm going to say it has coordinates, this one here, x1, y1, but I'm going to call it a vector. I'm going to say the vector to get from the origin to this point is the vector x1, y1. I'm going to say the position vector to get from the origin to this point here is x2, y2. And similarly here and here, I'm going to call this x3, y3, and x4, y4. Okay, and I'm going to draw a line in here to show the square. Imagine that's a square, even though it doesn't quite fit there. There we go, a bit better maybe. Okay, now I'm going to make these all I'm going to just group these here. Now, imagine I performed a translation on that shape. I moved that shape according to some vectors. Say I moved it 10 right and 10 up. That shape then might look something like, I move it 10 units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say I move it up there. Say it looks like that. Now it's got a new set of coordinates for each of its points. And I'm going to call these position vectors. I'm going to call this one, because it relates to x1, I'm going to call it x1 dashed. I'm going to call this one y1 dashed. I'm going to call this one x2 dashed. I'm going to call this one y2 dashed. And I'm sure you get the picture here, what I'm doing with all the others. I'm going to call this x3 dashed and this y3 dashed. And I'm going to call this x4 dashed, x5 dashed. Sorry, y4 dashed. Okay, so the reason I'm using those notation is just to say this point relates to that point, but it's been moved now. Now, I can represent this translation. I can call it a transformation T. And I know that when you put in x1, y1 into this transformation, out comes x1 dashed, y1 dashed. So this particular transformation, it's a translation, is a rule that maps each point to some new point in the plane. And I could say the same for x2, y2, etc. Now, this here, the position vectors I put in are called the input. And what I get out after I've applied the transformation to the input is called the image. Okay? And we can say, therefore, in general, that a transformation, what is a transformation in general? Well, a transformation is a rule, let's call it T, that maps points in the xy plane to points in the xy plane in the xy plane. Okay, it takes a set of points and it moves it somewhere else in the plane. And a translation does that, an enlargement does that, a rotation does that, and a reflection does that. So in general, transformation, some rule, and you might call it T, and you put a vector in, an xy position vector in, and you get some other xy position vector out. Okay, and that is a more mathematical definition of what these transformations you did at GCSE were about. Taking it one step further and introducing you to something called linear transformations. Linear transformations are transformations. Okay, so they are this rule that maps points in the xy plane to other points in the xy plane. But it has some properties, and the properties are this rule, when you apply this rule to the vector 0, 0, the point 0, 0, you always get 0, 0 back. That must be true. And in general, when you apply that rule to a general point x and y, what you get back for the x coordinate is some number of x's plus some number of y's, and for the y coordinate the exact same thing, some number of x's plus some number of y's. Maybe not the same numbers of these and different numbers. Okay? So that's what a linear transformation is. So going back here, a translation would not be a linear transformation, okay? Because if you took the point 0, 0 and you moved it, it wouldn't stay at 0, 0. So the only one that's not linear is this one. This is not linear. All the others, when you enlarge a shape that had a coordinate 0, 0, it stays at 0, 0. If you rotate a shape around the origin, then it would stay at 0, 0. And if you reflect a shape in one of the axes here, it would stay at 0, 0. So that's what linear transformation is. It's a rule that maps points in the xy plane back to points in the xy plane, and it has two conditions. When you take that rule and apply it to the origin, you get the origin back. You take that rule, apply it to any general point, and you get multiples of x and y back for the x coordinate, and multiples of x and y back for the y coordinate. And that's what a linear transformation is in general. Now, because when you apply the transformation to the coordinate x, y, you get this back. You may remember from our matrices knowledge that if you multiplied the matrix A, B, C, D by x, y, what would you get when you multiplied that out? Well, you would get AX plus BY, and you would get CX plus DY. Okay, so just by the way matrix multiplication works. So therefore, any matrix of this form, any linear transformation that when you put x, y in, you get this back out, this is equivalent to, thinking of this transformation, this is equivalent to a matrix multiplication. This is equivalent to a matrix multiplication. Okay, so in general, all linear transformations can be represented by multiplying by matrix A, B, C, D. Okay, so you therefore have a way of representing any linear transformations in terms of matrices. So let's do a few examples just to show you what I mean by this. Here is an example here. It tells you take a linear transformation and you put in x, y, and you get this out. It asks you for the matrix that represents that. Well, you put in x, y, and you get back, well, let's put it in the form ax plus by and cx plus dy. Let's put it in that form, okay, first of all. So how many x's? It's 1x plus 2y on top, and it's 3x plus 0y on bottom. Now it's in the form ax plus by, cx plus dy, that should be there. So the matrix that represents this is therefore the matrix 1, 2, 3, 0. Okay, and let's just double check that works. Just going along here. If I was to take the matrix 1, 2, 3, 0 and multiply it by x, y, what would I get? Well, I would get x plus 2y and 3x, which is this here. 2y plus x is the same as x plus 2y. So indeed, that is the correct matrix. Okay, your turn. Why don't you try this one here, pause the video, and see if you can find the matrix that represents this linear transformation that I've called V. Okay, firstly, putting it in the form sum lots of x plus sum lots of y on top and bottom, this would be no x's, subtract 2y, and 3x's plus 1y. So therefore, I'm saying that this matrix, I'm going to call it V, must be 0, negative 2, 3, and 1. And just to check that is indeed right, if I took 0, negative 2, 3, and 1, and I multiplied it by x, y, let's just check I would get this over here. Well, I would get indeed negative 2y on top and 3x plus y on the bottom. And therefore, I've got the correct answer. Okay, so what we've done is we've been given a linear transformation, we've been told the rule, and we have found the matrix. Now we're going to be given the matrix, and we're going to find what happens to points when we put them in this matrix. So I have a square with these coordinates here, and I want to find the vertices of this square under this matrix. Now, I want to apply the matrix M. I want to multiply the matrix M, which is negative 1, 2, 2, and 1, by each vertex of this square. So I'm going to put in each of these points as a column vector. 1, 1, I'm going to put in like that. 3, 1, I'm going to put in like that. 3, 3, I'm going to put in like this. And 1, 3, I'm going to put in like this. Okay, so I can find what happens to this square by multiplying it by this matrix, by performing this transformation on the square. Now, can I do this first of all? Well, yes, a 2 by 2 multiplied by a 2 by 3. I know I'm going to get myself at the end a 2 by 3. and let's just multiply it out and see what happens. -1 add 2 is 1. This times this. -3 add 2 is -1. -3 add 6 is 3. And -1 add 6 is 5. Then do the bottom. 2 add 1 is 3. 6 add 1 is 7. 6 add 3 is 9. And 2 add 3 is 5. So therefore, my square, which was these coordinates here, has now gone to these coordinates here. And I have found, and this was called the image, because it is the result of putting in these points and applying the transformation given by that matrix to those points, and I get out the image here. Now I could draw that out. This here was a square. Let's just very, very quick sketch, not accurate here. I had corners 1, 1, 3, 1, 3, 3, and 1, 3. I had something that looked like that, and it actually got transformed to 1, 3, so 1 across, 3 up. -1, 7, so -1, 7 somewhere over here. 3, 9, so be 3, 9 somewhere massive over here, and 5, 5, which would be somewhere here. So it actually got transformed to something that looks like this. Okay, but I haven't drawn that accurately. It's just rough sketch of that there. And that's all I wanted to say on this video. So, just to summarize, any linear transformation can be written as a matrix A, B, C, D. Okay, just going back to example 1, if you know the rule, if you know that xy goes to 2y plus x and 3x, then you write that in the form ax plus by and cx plus dy, and that's your matrix. You can find your matrix. And then, if you are told the matrix and you want to find out what happens when you apply that transformation to points, you just do a matrix multiplication. You take the matrix out in front and you multiply it by the position vectors of each of the points you're interested in finding out where they go. You do that matrix multiplication and it tells you where the image under that transformation actually is, i.e. the output of that transformation. And here's one for you to have a go at yourself. Have a go at these and just see if you can work those ones out. I'll go through in 10 seconds. Well, for part A, I would apply 2, 0, 0, 3 to the points -1, 0, 0, 1, 1, 0, and 0, -1. I would multiply that out, and with a bit of luck, I get -2, 0. This one here would be 0, 3. This one here would be 2, 0, and this last one would be 0, -3. So that's what you would get in that particular case for part A. That would be the image. And the same thing for B and C. It's just a case of multiplying those out. So 1 minus -1, 1, 1. I'm going to again multiply this by -1, 0, 0, 1, 1, 0, 0, -1. For the last one, I'll write it out and then do it all in 1. 1, 1, 1, -1, -1, 0, 0, 1, 1, 0, 0, -1. Just multiply these out and see what image you actually get. I'm just going to do this here. This row times this column would give me -1. This row times this column would give me -1. This row times this column would give me -1. This row times this column would give me 1. This row times this column would give me 1. This row times this column would also give me 1. and this row times this column would give me 1, and this row times this column would give me -1. And that is my image there. And the last one, therefore, I would do that row times that column, just to start with. So this row times this column would give me -1. This row times this column would give me -1. This row times this column would give me 1. This row times this column would give me -1. This row times this column would give me 1. This row times this column would also give me 1. This row times this column would give me -1. This row times this column would give me +1. And so we have the correct answer there. So they're the images. So for example, if someone asked you where did the point 0, 1 go to, well, the point 0, 1 went to 1, -1. And if up here, say they ask you where did the point 0, -1 go to, well, it went to the point 0, -3. And as before, that is therefore called our image, and this here again is our image. This here, these are our matrices, or our transformation. That's our matrix transformation, our matrix transformation, and these are our object. This is what we apply. We apply the transformation to that object, which was the vertices of a square. And we're done. And that's all for this video. So just to finish off with, I suggest you read chapter 4, page 82 to 85, and do exercise 4D, questions 4, 5 and 6. Thank you for watching.